Welcome to this video where we got to talk about the practice of laboratory of control, where we made a circuit of low-pass Sallen-Key filter of second order. First, we designed a low-pass Sallen-Key filter at 5 kHz using the TA filter design tool. Since only TNF capacitors were available, we adjusted the resistor values to keep the cutoff frequency close to 5 kHz. For example, with C and C2 to TNF, our values are about 3 kilo ohms. In the second part, we studied the stability of the circuit that we made, where we have to modify the feedback of our circuit, where we can change our gain. When we have these values of resistances in our feedback, the filter is stable but more resonant. With these values, the system becomes marginal with strong peaking and low ringing, and with this value, the system turns unstable, and in simulation we observe the self-oscillation. Next to this, we make a cascaded this stage with a first-order active RC low-pass filter implemented with a buffer of amp. Together, they form a third-order low-pass filter, and in simulation we confirm the stronger attenuation above 5 kHz and higher overall phase shift exactly as theory predicts.
As we can see on this breadboard, we have the following configuration. On the top part we have a first order not inverter amplifier circuit, and the bottom part we have second order Sallen-Key amplifier circuit powered by plus minus 12 voltage. The yellow signal corresponding to our first order filter and the blue one to our second order filter.
Of the lab, we analyze the transfer function of the system from the point C. The circuit is a second-order Sallen-Key low-pass filter. This is the transfer function, and the transfer function of the circuit received first order is this. When we cascade both, the total transfer function is this. In Scilab, we implemented this transfer function and tested its behavior using both plots and step response. Comparing with the electronic simulator, the results are very similar. The cutoff frequency match, the magnitude and fast response are consistent. Minor differences appear due to the ideal models in Scilab versus the real op-amp limitation in the electronic simulation. And we see the results of the simulation. Both second order, both third order, and step second order, step the third order, and we see the compared step response.
When we modify the feedback resistance, we are altering the circuit gain, and consequently is stable margin, and this way the system can operate under stable, marginal stable, or unstable condition. Depending on the choose value, the highlights the importance of carefully design the feedback network to ensure reliable filter operation and avoid unwanted oscillations.